Hey everybody, today I wanted to take the opportunity to talk to you guys a little bit about plotting enzyme data or enzyme data plotting. Um, and I'm just going to jump right in so that we can look at this data in a Michaelis-Menten curve as well as a Lineweaver-Burke plot. So if you remember from lecture, we did what was referred to as the Oreo cookie lyase experiment. So we had an enzyme, a person would be the enzyme, we had a substrate, and we had a product. So the enzyme was a person, the substrate was an Oreo cookie, the product was an Oreo cookie that had been split apart. Now, there's our information about that. Now, what ultimately mattered was we did a series of experiments. So we had basically two significant data points. So if you look at experiment number 1 right here, what you'll see is that we have a concentration. There were a total of 5 places that people were sitting, or you can imagine that there are 5 places that people were sitting at desks, and 1 Oreo was provided per 5 desks. So think about that like concentration. X many number of moles per unit volume. So we have a concentration right here. And so I'm going to write our concentration, or just letter C. Now, in the next column, what you see is the number of Oreos lysed in 10 seconds. So the production of a product in a time interval. So this was 3 Oreos were lysed in 10 seconds. So we have a concentration of a substrate. So how many, we have a concentration for our substrate, how many Oreos were provided per desk. Then we have the number of Oreos, the number of products that were generated within a specific time interval. So if you look at this, moving from the top all the way down to the bottom here, what you'll notice is the one thing that changes, the one variable that we could control is the concentration. And we're increasing the concentration, so we're providing more Oreos per desk. We went from 1 Oreo every 5 desks to 1 every 4 desks, 1 every 3, 1 every 2, 1 every desk. And if you watch that, ultimately we got to a point where there are 5 Oreos per desk. So think about it as if one person was provided with 1 Oreo, well, they're going to be able to make that product, and then they're going to have to wait for more of that substrate to be provided. Compared to if you had 5 Oreos to work with, they would do 1, and they'd immediately be able to grab the next one, and do the next, and so on. Now, what's significant about that is at some point, you can be provided with a large number of Oreos or a large number of the substrate, and no matter how much of that substrate you're provided with, you're going to be limited on the rate of Oreo lysis, or the rate of product production. And if you look at this data, what we see is that as we increase our concentration, starting at experiment number 1, our rate begins to increase. And our rate will continue to increase until we get to about experiment number 7. Now, at experiment number 7, if you look at that rate, and experiment number 8, look at the rate of that, experiment number 9, look at the rate of that, what you'll see is that the production actually kind of tapers off. So imagine this like a limiting reagent sort of problem that you saw in Gen Chem 1. If you had a balanced chemical reaction and you had a 2-to-1 molar ratio, so 2 parts of A, 1 part of B produces X many numbers of your product, you have a specific ratio. And at some point, if you provide infinitely more than what is, I guess, available, or infinitely more of one reactant than the other one, at some point, it doesn't matter how much you're providing. Your limiting factor is going to drive the production. And so if you look at this, what you'll see is sort of this tapering off. Now, what we're not changing in this is we're not changing the amount of our enzyme. Our enzyme is going to be fixed, and as we increase our concentration, we're not changing the amount of our enzyme. All that we're doing is we're changing the availability of that substrate, or the ability of that enzyme to get that substrate. And at some point, your product production is going to basically taper off. So what we see here is, well, at right around a 3-to-1 ratio, we're stuck at about 15 Oreos sliced in 10 seconds. So it doesn't matter if we went up to 100 Oreos per desk, we're still stuck at about 15 Oreos sliced in 10 seconds. The only thing that would change that is if we increase the amount of enzyme, but we're not doing that here. Now, with all of this information, what you can do and what you will do is you will plot it on a Michaelis-Menten curve, because a Michaelis-Menten curve is going to enable us to do a couple of things. Now, on our next slide, what you'll see is all of that data plotted. On our y-axis, we have a rate, and on our x-axis, we have a substrate concentration. And we'll be able to visualize that product generation or product production basically tapering off. So if you look on our y-axis right around, well, where our product generation was tapering off right around 15 or 16, you'll see kind of this data basically plateaus. So if you give 3 Oreos per desk, you're going to get a rate comparable to if you gave 4 Oreos per desk or 5 Oreos per desk. If you gave 6 Oreos per desk, well, that data point is probably going to be right here. It's not going to spike up or anything like that. Now, what this is characterized as and referred to as is your Vmax, your maximum velocity at which your enzyme can catalyze a reaction. Now, what's significant about that number is what is known as the Km. So what is the concentration of your substrate that gets you to half of your maximum velocity? Well, we can figure that out by looking at our y-axis and saying our maximum velocity is approximately 16 Oreos per 10 seconds. So half of that would be right around 8. Okay. Now with right around 8, where does that correlate with our x-axis? Well, looking at our x-axis, we're looking at something right around here. So I would put that at your Km is approximately, that would be basically 0.75 Oreos per desk. Okay, so a Km is a concentration where you're going to get half of your maximum velocity, and that's one way that you can depict this information. An alternative, and maybe a little bit more clear because it's a linear plot, is to take reciprocal values of your concentration. I've underlined both of those in red. You've taken your concentration and you've taken the reciprocal of that. And then in blue, what you'll see is this data right here, underlined in blue, I'm sorry, is your rate. So we've got our rate from that previous data, and we take the reciprocal of that rate. So this is just a matter of plugging in 1 over 5, 1 over 3. So 1 over 1 over 5 gets us 5, 1 over 3 gets us 0.3. Now, with that said, whenever you take all of this data that you've generated in these two columns right here, you plot it on what is known as a line-weave-revert plot. Now, what's great about the line-weave-revert plot is it gives you a little bit more concrete way of calculating your Km and your Vmax. And the way that that's calculated is by your intercepts. So this gives you a linear representation of all your data. And you can figure out the equation for a line, y equals mx, sorry, I'm writing with my mouse, mx plus b. And ultimately, you will have this line that extrapolates out through your y-axis and through your x-axis. So in your x-axis, your x-intercept is equal to -1 over your Km. Your y-intercept is 1 over Vmax. So what you can do then is plug in, or using this equation for, or you're using your equation for your line, you can plug in values for x and y and find out what your Vmax is and what your Km is. So these are both extremely important kinetic parameters. You should expect to see a question on your exam that asks you, given this line of best fit equation, y equals mx plus b, what is your Km? What is your Vmax? And whenever you are solving to figure out what your y value is, what you need to do is plug in 0 for x. If you are solving for your x value, your x-intercept, then you need to plug in 0 for y. Now, keep in mind, whatever value you solve for there, whatever this y-intercept is, that is equal to 1 over your Vmax. Whatever your x-intercept is, that is equal to 1 over Km. So do some practice problems like that. And whenever I say practice problems, I mean just come up with a y equals mx plus b. So y equals 35x plus 9. What would your Vmax be? What would your Km be? Solve for that, play around with that equation, make sure that you're comfortable with that. In addition to that, what are the definitions for Km and Vmax? Km is a concentration. So what would you expect your units to be for that? Well, Km, since it is a concentration, you'd expect units to be something like micromolar or millimolar, whereas Vmax, that is production of a product in a time interval. So that is a rate. So you're going to expect a two-dimensional value there. So your units would be something like micromolar per second, per minute, something where you're noting the production of a product and relating it to a time interval. All right, well, I hope this is really helpful for y'all. Have a great afternoon.